Origin and evolution of regolith on airless bodies, the role of thermal fatigue. And the talk is given by Charles Elmira.
Hello, everyone. Thank you for being here, and hello, and thank you for everyone joining us online through the live feed. I'm Charles Elmira. I'm a PhD student at Johns Hopkins University, and today I'll be talking to you about a project that is currently a work in progress, but want to present to you some of the primary results that we have, some of what's the directions that we're working on, and where we're going in the future. So the project we're looking at is to try to quantify the contributions of thermal fragmentation and relate that to the regolith origin and evolution. In fancier words, it's to study the variation of thermal fragmentation as a function of temperature range, rate, metrology, and grain size, and the size frequency distribution of resulting particles. Sounds much fancier when said this way. I realize most of you here in the room, if not all of you, are quite familiar with regolith production and evolution, but just a quick 1-minute briefing on what do we know of the regolith production and evolution. Regolith is basically this layer of fluids and rocks covering the surface of a certain planetary body. The most canonical method that we know is applicable for generating regolith is through mechanical disruption, and that is basically due to the micro and macrometeorite bombardment. So you have either a small-scale bombardment of meteoroids or a larger scale that will lead to obviously breaking down the surface of the material, leads to heating and melting of the surface material, and obviously its breakdown. Another model that's been proposed is thermal fatigue, which we'll be talking about today. Thermal fatigue is basically related to the day-night cycles. So you have a certain rock sitting on the surface of the planet, and the sun rises, heats part of the rock, you get heat transfer inside the body. The sun sets, heats the other side of the rock, you get heat transfer inside the body. Now this body is first of all very heterogeneous, so each individual component inside of the rock wants to expand more than the other. And you're heating one side of the rock only, which leads to some thermal conduction that generates transient thermal stresses. So you have one part of the body that's trying to expand more than the other, and one face of the body trying to expand more than the other. And you keep doing that on and on and on, until in the end the rock cannot handle all these different stresses and breaks down. So you get rock weathering and fragmentation, but with no subsequent ejection. Now, these are only two of many other models that are out there, but to explain why we're looking at thermal fatigue, we need to look kind of like head-to-head comparison. So the mechanical disruption, as we all know, it's been said and studied before, on the lunar surface, for example, rocks have limited lifetimes before being destroyed by micrometeorite impacts. For example, the 99% survival time of lunar rocks that are greater than 2 meters is about 150 to 300 million years. On main-belt asteroids, using similar models, rock survival time due to micrometeorite impact is about 10 times longer than on the moon. On near-Earth asteroid, it's almost the same as on the moon. And this is mainly due to the lower impact velocities that are in the main belt, around 5 kilometers per second versus 15 kilometers per second on the moon. And this makes the rock breakdown process less efficient. Furthermore, the crater ejecta velocities resulting from an impact event typically exceed the escape velocity due to the low surface gravity, such as on small bodies like Itokawa. Therefore, thermal fatigue has been proposed as perhaps being a dominant mechanism on these small bodies to disaggregate rocks. And it's been talked about before. I know Jamie Molaro, she's here in the talk, has studied this quite a lot. So we set up on trying to prove that, or disprove, prove or disprove, if this method is really efficient in generating regolith. So we know that thermal fragmentation from basic mechanics is driven by thermal cycling, as previously said, thermal gradients, and heterogeneities. So Marco Delbo set up a set of experiments in which he thermally cycled samples to understand how cracks grow as a function of compositions, grain size, thermal amplitude, and period. And in these experiments, he took two different, I don't know if you can see the pictures quite well, but In the red circle, these are before-after pictures from meteorite samples that have been thermally cycled. The red circle here contains no crack, and then in the arrows here, if you don't see it, just take my word for it, you will see crack that is propagated due to the thermal cycling. So under these lab conditions, we inferred that the crack growth would be about 0.5 millimeters per year. But before we get too excited about that, we all know that crack growth is a nonlinear function of the crack length. So if we just say that it's 0.5 millimeters per year, that means that a 1 centimeter rock will break down in just about 20 years, which isn't quite realistic. So we set off to model these set of experiments, and we used the well-established fatigue crack growth model, which is the Paris law, and basically relates the rate of change of the crack length per cycle. So A is crack length, capital N is the cycle, to two material parameters, C and N, and delta K, which is the range of stress intensities that we witness inside one cycle. So we use this kind of model. We set up a Regolith distribution, included a 30 micrometer crack on the surface of each rock, as circled here, and then kept doing on this cycling to see how these cracks grow per cycle. The results we got were quite interesting. First of all, on the first column and the second column represent two different types of meteorites. One is the ordinary conduit-like meteorite. The other one would be the carbonaceous conduit-like meteorite. The dashed line is the time it would take to break down this meteorite or a rock of a certain size, given on by the left axis, through micrometeorite bombardment. The red circles and blue circles are the time it would take to break down that same rock under thermal fatigue. And the error bars represent our uncertainties in the model, especially in the material parameters. So we can see that a 10 centimeter rock on the surface of a near-Earth asteroid, so this would be a near-Earth asteroid location, could fragment into smaller pieces through thermal fatigue in around 2,500 years. That's the spot here. And then there's the uncertainties, of course. And that is several orders of magnitude faster than comminution by micrometeorite impacts. Now, the trend that we see here is that as the rock size increases, the time it would take to break down that rock by micrometeorite impacts will also increase. And at some points, it's even maybe be faster than thermal fatigue. But on the other hand, in thermal fatigue regime, as the rock size increases, we see that it would take almost less time to break down the same rock. And this would be due to the higher stresses that we see and the presence of more heterogeneities in that rock, which of bigger size. Also, the speed of thermal fatigue is reduced at larger heliocentric distances, obviously because you have less heat delta T ranges, less temperature ranges. So moving on from this work, we currently have three main tasks, which is the modeling task, an experimental task, and testing through lunar images, trying to validate or disvalidate this kind of theory through lunar images. On the modeling side, we look to move from a thermal fatigue model into thermal fragmentation model, in which we try to account for multiple cracks and multiple crack growth, and the coalescence of these cracks in order to generate fragments, so we can get some kind of fragment size distribution. We would then look at the regular model that we know of, which is from the impact ejecta, from the micrometeorite and macrometeorite bombardment, and then try to couple these two models together to get a Regolith evolution model. For example, an impact event will generate some surface flaws that will in turn propagate due to thermal cycling. On the other hand, a thermally cycled rock that has cracks that grew up already will be much easier to break down through some kind of impact event. On the experimental side, we want to try to first get the thermomechanical properties of these rocks, of these individual chondrules, in order to use them as inputs in our model and in order to get rid of the big uncertainties that we have in the material parameters. So Dr. Kavan Hazali is a postdoc in our group. He's going to be running experiments on to get the mechanical fatigue properties of lunar samples, if you can get our hands on those. And we're looking at trying to get the coefficient of thermal expansion for the baseline materials, because these are the stress intensity concentrators. In terms of lunar testing through lunar images, we know that on the moon there are areas of permanent shadow. And we consider these areas of permanent shadow isothermal, and thus they should not experience this huge temperature range effect and these huge thermal cycling effects, thermal fatigue effects. These areas can be imaged, as we saw yesterday in some of the talks, and we can image them and look at the science frequency distribution of the rocks on the surface. And then, if micrometeorite impact is the only mechanism on the moon, this distribution should be quite similar to those of the illuminated areas. Whereas if its thermal fragmentation is important on the moon, we would expect to see different distributions. Maybe. We will have to look into that and see what we get. So as a conclusion, I'd just like to bring to your attention, this is the main topic of this talk, is try to get us to think about thermal fragmentation as being an important mechanism to break down rocks on airless bodies where the temperature variations may lead to thermal stresses and may lead to thermal fatigue. And we have shown that the thermal fragmentation due to these day-night cycles may break up rocks larger than a few centimeters faster than micrometeorite impacts. And this means that production of fresh regolith due to the thermal fatigue fragmentation could be an important process for near-Earth asteroid surface rejuvenation. However, further work is needed in obtaining thermomechanical properties of lunar and asteroidal constituent materials, again, to get rid of these uncertainties that we have in our models. And then we need to move on from a simple thermal fatigue model in which we are modeling just one crack growth and seeing how long will it take for that crack to grow, and look into the fragmentation aspect due to the interaction of multiple cracks, and then coupling this advanced model into the already established regular generation impact models and see what we could get from the combination of these two kind of models. That's all.
Jeff Taylor, University of Hawaii.
Oh, Jeff.
What's the effect of pre-existing cracks? Because these, the asteroid surfaces and lunar surface have already been reworked by bigger impacts. And
right.
So there's some there to begin with.
Right. So in our model, we assume that we have a 30 micrometer crack, and we started propagating this crack through thermal cycling. Thermal fatigue usually uses a pre-existing crack and then grows that crack on and on. So when you're working the fatigue regime, you're working less than the critical stresses that would be required to break down a material. So you need some kind of pre-existing crack to grow that, and then you could get some fragmentation due to this fatigue regime.
One quick comment. I saw Larry Taylor, University of Tennessee. I saw back here, one of the posters said something about thermal effects are negligible. Have you seen that poster?
I did not see that poster. If you could give me who gave that poster.
I wandered around and saw it.
Was it thermal effects on the moon or on asteroids, or?
It was just thermal effects for space weather.
I would need to know to look at what exactly they were looking at. Maybe it was more of a compositional effect. We're looking at breakdown of materials through thermal cycling, which is also something that we observe on Earth. It's not something far-fetched.
Bill Bodke, Southwest Research Institute. The timescales you're suggesting seem really fast to me. And I find the same way about Marco's results as well. I mean, here's some things that bother me, or that I'm thinking about, is that the time scale we have on the moon to break down rocks may be on the order of hundreds of millions of years, because of the diviner rock abundance. We have cosmic ray exposure ages on rocks and lunar meteorites and on lunar samples. We also have a lot of meteorites that have cosmic ray exposure ages of tens to as much as 100 million years. Now, they're small bodies in space, but they're a few meters in space. So I would expect, given this, you might get also some breaking down from things then. And we see rocks on small asteroids. So it all seems very fast. Is there a way to slow this down?
Actually, yes. If you account for multiple cracks and not just one single crack that is growing from the surface of the rock and crossing right through the diameter, you might get slowed down of this kind of mechanism. So this is why I said we need to move on into a more advanced model that will account for the interaction of cracks. Because if you look at it from a micromechanics-based modeling, you already know that if you have multiple cracks growing inside a body, one crack might shield the growth of the other crack and arrest that growth, and then you would get slower mechanism. So this is why we need to look for a more advanced micromechanics-based modeling.
Anyone else?
If you do experiments on lunar samples, I just want to ask how big a sample can you do this with? Because you may not be able to get a fist-sized sample.
Right. So this is one of the challenges that we're facing. But for getting parameters for our model for lunar samples, if I go back to the equations that were earlier, let me just show you. Is this working? Yeah. Okay. So when you're talking about, come on, that one. All right. So when we're talking about the fatigue crack growth, as mentioned earlier, we have two material parameters that we need, which are C and the exponent N. These parameters, we can get them through some kind of micro indentation mechanism. So you need really small samples and use a micro indenter to get, and you do fatigue experiments to get these parameters C and N. These are the missing keys, if you want, in terms of mechanical properties of the moon. So you really need small samples. That's it. All good?